Good morning, everyone. Thank you for joining. Superata, you seem to be mistreated by my software because I got the message that you were trying to connect a couple minutes ago, and I actually had to stop and restart the meeting. Not your issue. It's just sort of frustrating. All this fancy software, and it just systematically breaks. But it looks like we have a good turnout today, and I will start shortly. You can see my video. There's a big old wet spot on my shirt from all the seagulls that are in the harbor behind me. That's actually not the case. It's a consequence of attempting to drink coffee without looking at what you're bringing in the cup. So if you were able to witness it, I think you all would have had a great laugh as I take half a cup of coffee and throw it on my, hoping to get it to my mouth. Didn't even get close. But I didn't want to go fetch another shirt. So it's a little bit of laziness on my part. All right, so that stalling was intentional right there, and that was to get everything set up. Let me share my screen. I already have the recorder running, so the usual administrative stuff is pretty much done. In the email invite this morning, it said that lesson 11 yesterday was still uploading, and that's pretty much the case. I actually terminated the upload. They've been uploading for about 18 hours, and it got hung somewhere. So my usual excuse is I'm pretty sure it's my home internet is having issues. So after this lesson, and after I render this video, I'm going to actually shut everything down and reboot the whole network. And that usually works. So we're all learning about this digital work from home together. One of these days I'm going to ask you all what your opinion is of it. I'll tell you mine. It's initially attractive, but overall I don't really like it. But I have no choice right now. Okay, so very good. That's set up. And so today's lesson is lesson 12. You can see I've been fussing with the content server for a little bit. Oh, that's local. That's not what I wanted to do. Let's see if, oh, that's also going local. Well, I'm no biggie. This will get me, yeah, okay, that link is still there. So we're looking at lesson 12, and it's the first of several that I have intended on something called a unit hydrograph. A very sanitary sounding name for what's essentially just a transfer function. And today's lesson will be to introduce the idea, and there's a few R scripts that are contained in the lesson itself that will examine. They're not necessarily unit hydrographs per se, but they're intended to help illustrate the idea on what a unit hydrograph is. So at the end of today's lesson, you should never ever be afraid of a unit hydrograph again, unless you have to do it without a computer or software. It's literally a function. It's a key on a calculator, if you will. And if you provide the inputs, it produces an output. So let me switch to the other web browser. That's the one I wanted. And I already have the presentation up, so I'm going to leave this over here and begin. If at some point I either get too quiet or forget to share my screen, feel free to chime in and let me know. So here's the lesson, unit hydrographs. Let's begin. So the readings that are relevant are chapter 12 of hydrology, which was by Broussard. It's in the syllabus, and I use the Kindle edition because it's pretty cheap, but I refuse to pay what they're asking for a physical copy. The other one is Chow, Maidment, and Mays. Pages 216 to 225 would be a good reading for this topic. And in the FHWA-NHI2, or HDS2, which is called Highway Hydrology, I believe section 6 of that is what you would want to read. It's also worth reading for historical reasons. The paper by L.K. Sherman in 1932. So this is credited with the beginning paper of the unit hydrograph method. That's not strictly true, but it is the most recognized paper of the method. And then there's some additional links that are provided on the server. So there was a reason I wanted to go here. And so let's go there. Maybe my local machine is sputtering today. Lesson 12. So child movement means, oh, here it says 201 to 241. You'll be able to tell the right section. Here's Sherman's original paper. And if we look at it, it's actually kind of interesting historically because papers in 1935 are laid out much different than they are right now. So Sherman was a consulting engineer in Chicago, and the method that he demonstrated was largely graphical. Now that was a consequence of the computational tools at the time. Digital computers as we know them didn't exist yet. Well, I guess 30s, yeah, they didn't really exist yet. And there were analog computers and there were mechanical computers, but those actually required a very skilled machinist to just construct the computer. Think of it as actually writing the program. But you're writing the program by cutting pieces of metal to different lengths and hooking them up into gears. If you ever get to visit Berlin, there's a museum of industrial technology, and they have on display a circa 1930s era mechanical computer. It still uses binary encoding, but it's easily the size of a small car and has computational capabilities rivaling that of your watch. I mean, it's really, in today's context, it's a fascinating thing. So you should all get to take a look at it. I have some photographs of it somewhere. I'll try to work it into a lesson someday just for some interesting sideline. And so if you can read this on your own. Some of the key features of Sherman's paper is the idea of duration and concentration, or what later I call a characteristic time. And he's got some examples. He discusses BASEFLOW, has one for a particular river, and shows the computed and observed hydrograph. Now in the 1930s, there's no way they were making continuous. It's very unlikely they made continuous stage measurements. So this is still a cubic spline drawn through discrete points. But if you look at the plot, that's not too bad. Actually, we can't do much better today. And then here are the data that he used. And then here's another river that he studied, and actually get very good performance there. And then there's a discussion on the different shapes of unit hydrographs that are proportional to topography, storage in different locations. This too was a very important concept because up until the paper, developing a response function for a particular river basin, that wasn't all that hard. And in fact, that clearly would have predated Sherman's paper. But making the observation that the physical characteristics of the watershed itself changed the shape of the response function. And at the time, not a predictable way, but there was clearly a message here that if we could correlate shape, size, topography, storage, and what other metrics we could find on the watershed, there was a chance that we could predict these response functions ahead of time and not necessarily have to have observations. And to this day, that's now done. Functions like these, if they are inferred entirely from watershed characteristics, are called synthetic hydrographs. Synthesis meaning it's synthetic, meaning it's synthesized from things like watershed areas, slopes, what have you. Construction of responses based on observational results, a data science approach, those are called, that's called unit hydrograph analysis. So when you see the words analysis and synthesis, synthesis doesn't mean they're making it up out of the blue. Actually, they kind of are. But they're relating correlations of observed behavior to observed measures of a watershed. So this was actually a very important historical development in hydrology, certainly in engineering hydrology, but hydrology in general. And we get to the end of this paper, and so here's what I was pointing out, the difference in 1930s era articles and currently today. They just started the next paper on the same page. So that's not as common anymore. So Sherman's is a good read from a historical perspective. I don't think you'll find it terribly easy to read in the context of, I'm going to read this and I'm going to apply the method to someplace else. It was a different writing style back then, and I would imagine you'd find that hard. I certainly would. Let me get the second paper that's an important historical read. Was a contribution by a mechanical engineer. Actually, his area of research was thermodynamics. And this paper is important because it establishes the idea that there is a valid thermodynamics or statistical mechanical explanation for the unit hydrograph, which in turn was promising in leading researchers to believe that we could correlate physical properties of a watershed to the hydrograph distribution. Now this was likely a difficult read because it's assumed that the audience has a reasonable understanding of Boltzmann statistics and statistical mechanics. But going through it quickly, the discharge ratios, so Q dot sub C is a characteristic value. In our case, it's either a time characteristic, same thing here. It's also a magnitude characteristic, which would be our total storm depth, if you will. And he's saying that the ratio in time to a peak characteristic value is some function. And further it goes on to postulate that function is going to approximate a Maxwell-Boltzmann distribution, which is shown here. And then from that, a series of statistical analysis, actually probability analysis, of what a Boltzmann distribution should look like leads to ultimately try to get to the end here. This is pretty close. A hydrograph distribution. And this paper doesn't tell you how to find these characteristic times, but it does demonstrate that if you have them, there's the final hydrographs distribution, either in that form or this form, depending on the magnitude of an exponent. And you can see some stuff here that I wrote years ago, long time ago. But the result are shown here for a couple of watersheds, a couple of storms. And like Sherman's work, it's not bad. And so these were the historical papers, and then the benefit of Lienhardt's paper is by associating it with a statistical mechanical distribution, we're able to study the effects of different parameters of the distribution. And the key things here in his distribution is this exponent that he demonstrated would change depending on a fan-shaped watershed or a long, slender watershed. And then there was subsequent work to try to quantify what that exponent should be under those different conditions. The other important feature was what characteristic time to use. So Lienhardt used root mean square time, but one could just as well use a arithmetic mean time as the time characteristic. So that's some historical background. And then in '72, Lienhardt condensed the results. Hopefully this is the paper I want you all to have access. Yes, okay. So here is equations 3, 4, and 5 constitute what has become called Lienhardt hydrograph. And what's important is it turns out that they're a generalized gamma distribution, which is well documented and used in the literature. And here we see the effect on fan-shaped watershed on the exponent here, and a long, slender watershed where the exponent becomes 1. And in some instances, the exponent goes greater than 2, although that's hard to come up with a understandable shape that causes that in the real world. So that's our theoretical background for the unit hydrograph. So it's not just a function of convenience. There is some meaning behind it. So as we, before we continue further, let's discuss the idealized hydrograph that you see probably in every hydrology textbook in the history of the world, and some that haven't even been written yet. So a hydrograph is a plot of paired time discharge values. And nowadays it may not be a plot, but it's a set of paired values. So there's a time and a discharge associated with that time, and we have a collection of those. Usually it's monotonically increasing in time, because otherwise it doesn't make any human sense. And the idealized hydrograph depicted in here, go ahead and make it a full screen, has a couple of portions. So there's this portion in time where the discharge is declining as time increases. So think of it at basin scales. The basin is slowly draining. That's water probably coming from groundwater. And then there's an input of water, a storm, if you will. And that input causes the hydrograph to start to rise. So go ahead and put, so maybe there's some rain right there. And to make it meaningful, let's have some other rain right there. And I'm making no attempt to get the heights of the blocks to make any makes sense. But so we have this portion where there's some new input, and all of a sudden at the observation point, we see an increase in discharge. And then it increases up, in the ideal case, to a peak flow point, and then it starts to come down, and the declining or the recession limb may or may not begin after the rain is ended, but most likely after the rainfall's ended it will start to recede, or at least if the rainfall rate has dropped considerably. There's an inflection point where the curvature goes from curve down to the radius of curvature moves from here to this side. So it's curved downward here and curved upward here. That's called an inflection point. And that has some utility in subsequent conditions. And then this falling side is called the recession limb. And eventually we return back to our long-term, slowly receding discharge. Imagine we have a centroid of this hydrograph. The characteristic time of the watershed is usually taken as that distance. I'm going to call it just some characteristic time. What I've drawn here is actually basin lag time. There's several different names and there's several different starting points, but the distance in time between the peak and some starting point is the characteristic time of a watershed. And it will depend on the context of any analysis or science method that you're using. And they're all, if you know one, you know the rest. So the idealized hydrograph has a rising portion, a peak, recession, and an inflection point. And in this particular hydrograph, also has a base flow component because we're not starting at zero. We have some flow in the stream before the storm begins. So in many analysis, the first step is base flow separation. And there's quite a few different computational or operational approaches to making that separation. The method displayed in this diagram is called the constant discharge method. And it takes its name from when the hydrograph begins to rise, we declare the discharge the moment it begins to rise as the base flow separation. And you can think of us as extending a line across this hydrograph. Everything on this side of the line is base flow. I'm not going to. And everything above is storm flow. And so that's called the constant discharge method. That method has some attractiveness for automated and semi-automated separation. And it is likely a relatively commonly employed method in practical application. A second method is called a constant slope method. And in this case, we're starting at the same beginning point, but instead we extend that line to the inflection point on the recession limb. And everything below it is base flow. Everything above, storm flow. If you recall from our lesson last time, when we showed some real hydrographs, real hydrograph data isn't always as clean as this idealized hydrograph. There can be multiple peaks, not very far apart from one another, and so finding an inflection point can be a practical impossibility. In the absence of a really clean idealized hydrograph, I would argue that this method is not always or not commonly used. A variation of it that's even more elaborate is called the concave method. And here again, starting from the same beginning point, when the flow begins to rise, we extend a tangent line to the pre-storm flow down to a point beneath the peak, and then another line segment from that point back up to the inflection point. And this shares the same difficulties as the prior method, in that with real storm data where there's a lot of variability or multiple peaks, this may be quite impossible to accomplish. Nevertheless, this is used in idealized studies, and not all real data are as multi-peaked and ugly as I showed you all for Ash Creek. Every now and then, when we're doing a unit study and we're actually collecting data with the intention of understanding the hydrologic response of a particular gauging station, if you will, every now and then we get storm and discharge flows that are as clean as this diagram. And so those are immensely valuable from a scientific and engineering analysis perspective. But not always, and we can't predict when that's going to happen ahead of time. So there's several more ways to accomplish base flow. Probably a elaborate method that's in some of your older hydrology books is called master depletion curve. And this is a basin scale approach. So this requires multiple years of data, and you have to, the analysts have to select particular storms from that multiple years of data. And they're lined up in a time agnostic order. And from that you can determine how the basin drains in the absence of storm flow. And usually it's a decaying exponential. And the exponent, there's a factor in the exponent. So usually they're like a Q0 e to the minus kt, something like that. That k, that constant k, is what's sought from this analysis. And then from that point forward, from any known flow in the basin, especially if you know it's not storm flow, you can use that to determine what the base flow would be several months into the future, and then apply that to your storm hydrographs to do base flow separation. It's actually a far more elaborate problem than you could possibly imagine from anything in writing. Another approach is continuous simulation techniques, which I would qualify as being very much a master depletion curve method. SWIM is a good tool for that. In fact, it was built to do continuous simulation. And so you can think of it as applying SWIM at a watershed scale. And not like we did yesterday, where we took a watershed of 7 square miles and modeled it as a single subbasin of 4,000 plus acres in SWIM. But actually a watershed scale model of something implemented in SWIM, which would likely have multiple subcatchments and multiple hydraulic routing elements, multiple streams in it. For most practical cases with multiple peak hydrographs, I contend that the constant discharge method is the most straightforward to apply and is in all likelihood the most commonly applied base flow separation technique. Okay, so we've belabored base flow for a little bit on purpose because the unit response models, by definition, don't explain base flow. So in either simulation or analysis, we have to account for the base flow independently of those. So let's suppose we've done that. So now we have, let's say now we have the rose-colored hydrograph as data, and we slide everything down on the discharge axis, so the zero discharge corresponds to this line, and we can jack everything on the time axis to the left. So you can think of our storm flow hydrograph as looking like this. It's supposed to be the same. So here's the storm flow hydrograph. So we've moved this way and moved it that way, and we've tossed away the base flow. So we're not neglecting base flow, we just don't use it in subsequent analysis. We'll reassemble the two time series later to produce a total runoff hydrograph. So now we get to the topic of today. What is a unit hydrograph? How are they used? How are they made? And how do you synthesize them from simple watershed descriptions in the absence of gauge data? That's a long bullet item. We will attempt to answer these questions over the next several meetings. So we'll start, number one, with what is a unit hydrograph. So unit hydrograph is simply a function. Its purpose is to explain the time redistribution of excess precipitation on a watershed. Now I'm going to draw on this slide. Let's say we have watershed right here, and there's the outlet. So we rain on it. Got to rain on the parade. We consider this raindrop. It doesn't have very far to go to the outlet. But this raindrop here has quite a bit longer distance to get to. And so the unit hydrograph function is a tool to account for the different locations of arrival of rainfall. So that's what I mean by time redistribution. We have this rain, imagine if you will, uniformly applied on the watershed. So it comes in, and some instant later, all of a sudden, there's watershed depth. Well, for that depth to leave the watershed, it's got to flow out the outlet. But this portion up here is going to take quite a while to get to the outlet, or the portion that's very close to the outlet can easily get out of the watershed. And so the unit hydrograph function is a function that accounts for those travel times, if you will. So the unit hydrograph function also represents the response of the watershed at the outlet to a unit depth of excess precipitation. So excess is in all caps here for a reason. It implies that some kind of loss model has been applied to the raw precipitation. So the unit hydrograph only represents the water that can get out of the watershed. Water that's held in storage, that's lost to infiltration, that's returned to the atmosphere through evapotranspiration. Those are our main processes, are not part of the unit hydrograph function itself. They're accounted for before and after the fact, and if necessary, reassembled into the time series. The time redistribution implies some kind of transfer function behavior is applied. So there's words on what the unit hydrograph is. That's not a terribly useful definition, but it condenses all the ideas in Sherman's 32 paper and subsequent papers by Lienhardt and others. So let's look at this response model idea. So I'm going to take an excursion away from strict unit hydrograph theory and use a fluid mechanics approach to try to explain what a unit hydrograph is accomplishing for us. So visualize a watershed, if you will, that's loosely represented by this sketch. So it's a rectangular watershed. Think of it as a tank, a big tank with sidewalls, and the only way water can get out is through a slot at one end. And that slot in this drawing has a width of B. The plan view area of the watershed is labeled area, so It could be 100 feet by 100 feet or 200 by 200 and so forth. Even though I've drawn it here as roughly a square, rectangular is good enough mental image. And then we have inflow coming into our watershed, represented by the red arrows labeled precipitation. If we want that as a volume, the precipitation multiplied by the area is the volume that enters the watershed at some instant in time. If we can pretend temporarily that the slot is somehow covered up, if that inflow volume enters the watershed and it can't get out, then that water has to be stored on the watershed. And the total storage at any instant would be the depth of water on the watershed multiplied by the area. Okay, so far so good. That's just filling up a bathtub using the shower. Now let's examine the slot. If we were to pretend that we have essentially critical depth outflow, the amount of discharge leaving is going to be the flow area of the slot, which would be the width times the depth, BH, multiplied by the velocity of the flow passing through the slot, which the simplest model we can come up with from our elementary fluid mechanics would be a Bernoulli type velocity, which would be the square root of g times the depth, square root of gh. And we collapse all those terms into this single discharge function q. So here we have q equals the square root of b squared gh cubed. So that is our response model for a very geometrically simplified watershed. So now we'll make a couple of assumptions. First thing is, you can ignore the first assumption because we're using a slot, not a circular pipe. The outflow rate is determined by the depth of water in the tank at any instant. And back in your fluid mechanics class, you would have had a homework problem, or at least a lecture presentation of time to drain from a tank. It's a classic fluid mechanics problem. It's probably done in every fluid mechanics class in the history of the world because it allows the instructor to introduce the concept of the continuity equation in the Reynolds transport theorem and the energy equation simultaneously. And then they use a Bernoulli, modified Bernoulli's equation to explain the change in velocity from the free surface to the outlet. And you all have done something like that. You may not remember it, but you did it a long time ago. So we're modifying the classic problem in the sense that we can add water to the tank through the rainfall. So water getting to the tank will initially pretend that it can get to the outlet without any delay relative to the time intervals of interest. And the precipitation depth is uniform over a time interval, also spatially. So if there's 1 inch of rainfall onto the tank, it occurs 1 inch everywhere. If we take those assumptions in our original drawing, we can come up with a very simplified updating scheme. So this is no longer hydrology, this is hydraulics. We would set the initial depth equal to some value h sub 0, and the discharge at any time t plus delta t is equal to some discharge coefficient times the square root of all that stuff in the radical, b squared g times the quantity h of t plus delta t multiplied by the quantity p of t times a minus c sub d b squared gh cubed t over the area of the tank, quantity cubed. So all I've done is taken the original equation and made a fairly simple Euler method a prediction scheme. So delta t's have to be kept pretty small. The important thing of this isn't the equation itself, because if it were, this would be what we would would have been using for the last several hundred years, but the ideas that are embedded in the equation. So here we see discharge is a function of whatever's in storage at the time. It's a function of some watershed properties, which are the area of the tank, and B is the slot width, the area of the outlet. And it's a function of the incoming precipitation. And once we have Q at T plus delta T, we can update the current storage and proceed forward. And so we can put this into an R script and examine some interesting behavior. And so I have it in slides, but I'm going to attempt to use the actual R script to oh, it's still there from yesterday. Well, I hope I don't regret this. Well, actually, this is perfect, completely unintentional, but we'll take advantage of it. Here's what I meant by inflection point in these receding limbs will be phenomenally difficult to locate. Plus, there's actually no base flow in these models anyway. But that's what I mean by the multiple peaks. So that idealized hydrograph was just that, the idealized hydrograph. Let me go ahead and terminate all this. Okay, so I want to get okay, looks like I don't have R scripts built yet. No problem. Okay, I'm going to get a couple of R scripts that we have in the content server. They're already there, and I hope they work because I'm depending on that being the case. And there's no point in me downloading Excel files to share Hydro because it doesn't have an Excel implementation working. There'd be no way to do anything with it. But I do have R scripts. So first I'm going to take the tank analogy simulation. I want the slot model. And I want these three precipitation. And we'll get the unit hydrograph examples shortly when we need them. Okay, so this says in downloads, there's an R script. I can delete that guy. Hope I didn't just screw up. Cool, we didn't. So I'm going to open up the slot model for the tank, and I'm going to make it bigger, and we will examine it and then run it. So this is used to illustrate the idea of input transform response for unit hydrographs. This particular code is not itself a unit hydrograph. It's simply a time drain model for a peculiarly shaped tank, but it will illustrate the ideas that are necessary. So we have three prototype functions. One is called the outflow function, the other one is the inflow function, and then there's a change in depth function. The outflow function takes the output width, which was that slot width, which was B in the presentation, the outflow discharge coefficient, which was C sub D, the current depth of the water in the tank, which was capital H, and gravity, the gravitational acceleration constant, which is G, and computes the outflow rate. And let's look at the equation. It says it's C sub D multiplied by the square root of the width, B squared, times gravity, times depth cubed. So it's identical to this equation. So it's calculating the outflow. The inflow takes the precipitation, multiplied by the watershed area, and produces an inflow. And so watershed precipitation times watershed area is the inflow. It's identical to this expression. I didn't want that to happen. It's identical to this expression right here. Inflow equals precip times area. And then the change in depth is inflow minus outflow equals change in storage divided by the area that gets the change in depth. So it takes precip, area as input, the output width, the output discharge coefficient, the current depth, the time step length, and gravity, and computes a change in depth. So this basically is doing the change in storage with respect to time equals inflow minus outflow, and then it's multiplying by delta time, so it gets the change in storage equals delta time times inflow minus outflow, and then it divides by the watershed area to get the change in storage expressed as a depth. So we have the delta time, we have the inflow function minus the outflow function divided by the area or the scale of the process. So there's the three prototype functions. And now we will go ahead and perform a finite difference in time step through the rainfall runoff process. And it's basically an Euler type method here. So this first part is to this is a function for aggregating vectors. So that should be up in the prototype function. And now we'll go ahead and define physical sizes. So let's use a watershed that is 210 feet by 210 feet on the side, and I've done it as a square root of an acre. The watershed area itself is equal to length times width. The output width in this case is 1. We're going to change that. The output discharge coefficient here is 3600. In this case, the discharge coefficient is being used entirely to convert seconds to hours. Gravity is 32.2, so this is clearly going to be done in U.S. customary units. And I've chosen delta time as 1. So I don't know, thinking that's probably hours, not seconds. And now we're going to read from our precipitation files, the input precipitation. We're going to build the precipitation vector. And then we will start the elapsed time in hours. And we'll compute the depth. We will prepare a vector for the depth. We will prepare a vector for the output. And we'll start stepping through the time step equation using those various functions. Then we'll calculate the outflow, and in this for loop right there gets the watershed depth, and this outflow loop is computing the outflow. And then there's some plotting information down here. So let's look at this input thing. I'm kind of hoping this actually works. Okay, so it was set on precipitation 3. I'm going to do precipitation 1 first. So here's our first precipitation vector. So at hour 0, nothing's going on. At hour 1, there's 1 unit of input, and that's it. It's a very stupid-looking vector. Well, I sure didn't want to do that. So let's change this to precipitation 1. And we'll save. Go ahead and run everything up to that point. Now we're reading the precip. So now we've prepared an empty depth, and we're going to go through all the times, and we're going to calculate the watershed depth, and you'll see that it's dependent on the delta depth function. Now we'll calculate the outflows associated with those depths. We've actually already done those. They were embedded in the depth function. Now we'll prepare the plots. That's a warning to me to make room for them. I hope that's enough room for the plots. You see, it's a 1 by 1, so it should fit. It didn't generate the plots. See if it generated errors. Aha! Let me put the working directory into the correct place. Let's save that. There we go. It wasn't reading the file correctly. So now if we look here, here's our watershed depth and a watershed precipitation now converted into a volume, and then here's the outflow. So at time 0, there was nothing there, so there's 0 outflow. At time 1, we get the initial input, but because we're using a very naive finite difference scheme, that water has to be stored before it can generate outflow. At time 2, it's starting to generate outflow. At time 3 and onward. And so our red diagram is the input in cumulative space. So that single impulse comes in and then there's nothing new added, so it flatlines. The blue line is the outflow in cumulative space. So initially it's steep, so we get outflow and then the outflow rate decreases. And then the gray line here is what's in storage. So that first pulse of rainfall comes in, fills the tank to a particular depth, and then it starts to drain over time. Now let's change a watershed property. So we'll actually match the pictures over here. So 6-foot slot. So I believe the one in the presentation that uses the number 6. Save it. So I'm going to rerun the simulation. The general characteristics will look sort of the same. The red line shouldn't change shape at all. But with a 6-foot slot, you expect the storage to decrease a lot faster, and so this blue line is going to be a lot steeper. Ta-da, we're right. And so the only change we made was a single geometric change, and our response behavior has changed. Let's now try a different, and here in the presentation, the precipitation and outflow in the incremental space are plotted already. And I don't think I surely have that. That's time cumulative. If we want to look at it in incremental space, I think if I do that, there we go. So there it is in the usual hydrograph space we're familiar with. So 1 inch of depth coming in, we have 0.8 of a watershed inch going out in the first time increment, and then a little bit more in the last time increment, and then our system gets born. So now we're going to modify it by having an identical input at hour 13. So there'll be this first red pulse, and then there'll be a second red pulse, and we're going to examine what the outflow looks like in that instance. And we do that, in this case, simply by changing the file name. I think precipitation 2 is the one I want. I'm going to take a shortcut here and see if I can. So now we've got the second impulse. I chose hour 13 not at all willy-nilly. It was about when the storage had gone pretty back close to 0. So these two look like they're operating independent of one another. The presence of the first doesn't appear to affect the presence of the second, which is not true, but that's how it looks. And if we look at it in cumulative space, there's what it is in cumulative space. So here's our first input, second input, here's our response, and then the second input causes a second response, and the gray line is what's in storage in our simplified hydraulic explanation. Let's change the, let's change the rainfall time series one more time. So we're going to use a slightly different one, which is rainfall series 3. And we'll take a look at rainfall series 3 before we run it. Rainfall series 3, we have 1 at hour 1, and we have 3 at hour 13. So our second pulse is 3 times bigger than the first pulse. So if we think of this in cumulative space, we'll get this one height, and then we'll get 1, 2, 3 heights over here. So it's already saved. Should be able to get by with just doing that. And here we can see our one pulse and then the pulse that's 3 times high. And actually it's plotting off the axis on runoff. And if we go look at it in cumulative space, it looks like that, which looks a bit odd because we're getting more runoff than rainfall, and that is a consequence of the time step that was selected. So let me go to my last example. One foot tank rainfall time series. Yeah, first I want this one to work right. So let's switch it to 1 foot. And once we modify the geometric properties to fit within the time stepping. So an important critique of the finite difference approach used here simply to illustrate the idea is that it's extremely sensitive on the choice of time step, and it would be a bad modeling tool to use in a real case. So when the slot is made narrower, so when stuff has to stay in storage longer, we get the 1 unit and 3 unit case, and then we get the runoff from the 1 unit and the runoff from the 3 units. So let's look at it in incremental space because that's easy enough to do. See, it should be, yeah, it should already be there. So here's what it looks like in incremental space. So we have these 2 pulses coming in. The second one is 3 times bigger than the third one. And if we look at the height of the peak discharge just after the pulse, this is maybe 0.2. If we go to 0.2 times 3, it would be 0.6. In unit hydrograph, it would be a linear increase. This particular model is slightly nonlinear, so we get a little bit higher out here. But again, we can see the behavior that the second part of the storm just adds into storage of the first part and generates its own response. And then we want to use change watershed properties. So I think we've illustrated that. So here's the whole point of that example of those R scripts. The fact it's nonlinear is not the point. The observation of the computation scheme is time step sensitive initially seems like a critique, but it's actually quite consistent with unit hydrograph theory, where the characteristic time governs the entire behavior. In this example, there was actually very little time delay. Inputs can get to the output immediately, which is somewhat unrealistic when compared to real hydrographs. But here's the important part. So we can write that function at the outlet, the blue line. The blue line is Q of t is some function of precipitation, watershed area, initial watershed storage depth, how big that slot is, and any loss terms, which in this case are none. So a unit hydrograph is simply a particular type of this function f. So I'm going to go ahead and, actually I think I'll leave that running because we're going to need it in a second. So we'll return to the presentation, and if connected ponds like that over the years had proven to be a reliable model of hydrology, that's what we would be using. Turns out it's not, although there are ways to modify what I presented there, and that's pretty much how we would use swim as a hydrologic model. So we modify the hydraulics to be a little bit more correct, and we can use that in lieu of a hydrology model. But for the time being, we're going to look more at unit hydrographs. So our response models do the following. Imagine this picture, if you will. We have precipitation shown here as a big red ellipse falling on a watershed, which is shown as a green ellipse of the same size. And that watershed imposes losses on that precipitation signal. It takes a portion of it out as storage. The remainder is routed and transformed to the discharge. And so we have these blocks coming in, which produces our discharge function going out, and we're studying the transformation behavior. Another way to picture it is with this diagram, is that the response models convert the excess precipitation signal into a direct runoff hydrograph at the point of interest. And this block model is actually very descriptive of how this is occurring in a computational environment. The precipitation signal comes in, the big red arrow. It's forced to be filtered through a loss model. And so that green arrow that represents losses, those would be evapotranspiration losses, infiltration losses, water that's directed to storage that's not going to leave the watershed anytime too soon. And what's left is the excess precipitation. That's applied to a transformation model so that its temporal behavior matches what we observe as the runoff hydrograph, which is the blue arrow labeled runoff. That transformed box is the unit hydrograph. So we're going to look at yet another picture. So here's our precipitation. So Puffy the cloud is producing our rainfall. It falls onto this watershed, which has an outlet. A certain portion of that excess rainfall has to be stored on the watershed as, think of it as average depth. Then there's a lost portion that's removed from the signal, and then that all starts to drain out the outlet. And because the outlet's smaller than the entire watershed, it can't all get out at once. And so there's a delay between the input and the output. So here's our input signal of time width, capital D. Think of that as the duration of the rainfall impulse. There's the loss term applied to it, and that's whacked off the top. And so what's left is this purple excess. What we see at the runoff or at the outlet is at time zero, nothing. At the end of the duration block, there's now a little bit of runoff, and that's the first portion of the precipitation signal after loss has been accounted for. That's accumulated and is starting to run out of our watershed. And then we see over the next time block another portion, a little bit larger. Next time block here, another portion, and another portion. So in this diagram, the impulse duration is capital D, but the runoff time duration is 1, 2, 3, 4, 5 of those. And that runoff duration time will change from watershed to watershed. It's generally invariant within a particular watershed. In fact, it has to be for unit hydrograph theory as normally presented. So some watersheds will have a time base of, if it's 1 hour input, maybe 6 hours of output. Other ones will have 1 hour input, will make 11 hours of output. It'll change from watershed to watershed. But once you're talking about a particular watershed, that time base stays the same for the duration base. The distance in time from the beginning of time to the largest discharge is called T sub P, time to peak. The distance in time from the centroid of the impulse, or if it's a series of impulses, to that peak is called the basin lag, and the usual symbol is T sub lag. So in this diagram here, there's quite a bit of information presented. There's the impulse duration. So when we talk about a 1 hour unit hydrograph, we mean a unit hydrograph for some watershed for an impulse duration of 1 hour. We have a loss component. We have a basin lag, which is the distance from d over 2 to the peak. We have a time to peak, t sub p, which is the distance from time 0 to the peak. And we have a time base of runoff, t sub d, which is how many hours that runoff will occur caused by this single initial impulse. And the unit hydrograph approach, or the function, is typically broken into 3 components. First, there's the loss part that we've already examined. There's an initial abstraction and then an ongoing loss. It produces an excess rainfall signal. That excess rainfall signal is what can become the unit hydrograph. So there's a mathematical process called convolution between this red area and this green area. That produces a direct runoff hydrograph, which is the responses to each of these impulses added together in time. And that's put back on top of the base flow to produce the total runoff hydrograph. So a little bit of background on the different parts. If the pulses immediately went to the outlet, we would expect the direct hydrograph to have an identical shape as the input rainfall distribution. So on the left of this figure, the intensity impulses, the loss model's been applied, and then they're all pushed down to the intensity equals 0 axis on the lower diagram. And if there was no delay, then the intensity input would produce a runoff diagram that looks identical to it, only in this case it's changing color from red to green. But in fact, even if the pulses are uniform over the entire area, those that are close to the outlet will arrive sooner than those that are far away from the outlet. Thus, there's time redistribution. And that's represented by this transparent green hydrograph in the back. So if there was no time redistribution, red would make green, but because there is, everything's actually shoved a little bit to the right on the time axis. And this next picture shows that here. So now the transparent green pulses have been redistributed in time to produce the solid green blob, which is the direct runoff hydrograph for whatever watershed this is. And the unit hydrograph is the function that performs that mapping. The total hydrograph then is the algebraic combination in time of the direct runoff hydrograph and the base flow hydrograph. So the direct runoff hydrograph is that green blob in the upper picture, and it's added onto whatever base flow we had to produce the solid blue line in the lower diagram, which would be the total hydrograph. And the total hydrograph is usually what we're going to be interested in. Some other assumptions of unit hydrographs: the direct runoff duration, that D, is the same for all uniform intensity storms of the same duration. 2 excess hydrographs of the same duration will produce direct runoff hydrographs of the same duration, but with runoff rates proportional to the volumes of the excess hydrographs. We kind of demonstrated that in that R script, where the storms that were 1 unit high and 3 units high almost produced a tripling of the response. Because the example is nonlinear, that was not the case. But in unit hydrograph approach, we stipulate that it is the case, and it reduces the set of available functions we have to worry about. The time distribution of direct runoff from a given storm duration is independent of the current runoff from prior storms. That's an important concept, in that an impulse produces a response. The next impulse produces another response. Those two responses are added together in time. The existence of the first response has no effect on the second response, and vice versa. The existence of the second response, well, I guess that's going backward in time, doesn't affect the first one. And this leads to a signal processing concept called no memory. It means that the watershed has no memory of its prior condition. That's probably wrong in a strict scientific sense, but it's proved to be a useful stipulation for explaining the behavior of watersheds. So here we're going to try to look at those three statements pictorially. The direct runoff duration is the same for all storms of the same duration. So all storms that have length of this red line produce a runoff response of green line length, regardless of how tall they are. Two excess hydrographs of the same duration will produce direct runoff hydrographs of the same duration, but with rates proportional to the volumes of the excess hydrograph. So what that means is that this set of hydrographs is this high, produces a response that's that tall. If we double everything, then the then the height of the green blob doubles, but the time base does not change. And in terms of calculus, the integral of the excess precipitation signal in time is equal to the integral of the discharge signal in time. And then 1 over A is the watershed area. This is what scales between the two. So precipitation in inches, watershed runoff in watershed inches, and in cubic feet per second. If we divide out by the area, we can get it into watershed inches. The time distribution of direct runoff from a given storm is independent of concurrent runoff from prior storms. So what that means is, let's say this particular storm right here produces this green blob. Now we put that particular storm and another storm just like it, and they're going to share the last block. They're going to be common in the last block. So the actual intensity is up here somewhere for that block. All that means is that we can take this first response and we put it here in the time axis. We take the second response and put it in its appropriate location in the time axis, and then vertically add the two, and it produces this, in this case, this green line. It's kind of bimodal response. The presence of this first response doesn't affect the behavior of the second response. So the second response doesn't magically get narrower or taller just because of the existence of the first response. They do add together in the in the runoff axis once they've been lined up correctly in time. Each unit of hydrograph has a duration associated with it, which was capital D in the diagram. And if we're doing it using discrete techniques, that duration has to coincide with the time step size. If we do it using some other techniques, that requirement is relaxed somewhat. But it's best to keep that in mind. So a d-hour unit hydrograph is a response to a d-hour pulse of excess precipitation. And the flow associated with that response is reported every d hours until there's no further response, what I call T sub d in the diagram. Each watershed has a characteristic response time, the lag time or the time to peak. And the characteristic response time is thought to be related to physical characteristics of the watershed, contributing area, slope, and so on. That second bullet item is huge. That's what allows us to synthesize watershed behavior without having observations. Let's see, the time step for aggregation must be the same as the duration, and the time to peak for the watershed must be an integer multiple of that volume. That requirement's only true when we're doing discrete calculations. There's computational ways around that. And what that computational step is called convolution. And there's two types. There's excuse me. My allergies have been killing me. Let me check the time. Yeah, that's what I was afraid of. Let me look for the next slide. I'm going to stop with this slide. I'll finish talking about it. And what we'll pick up next time is with an example from Chow, Maben, and Mays. So continuous convolution is evaluating this integral. R is the rainfall or the forcing function. Think of that as the rainfall, the precipitation function. And it's a function of time. Script f of time is called the hydrograph kernel. So the discharge that we see from a watershed in continuous convolution is the integral from 0 up to some time of interest of r of tau times the kernel f of t minus tau d tau. If you're not familiar with convolution integrals, it looks like an integral, but it's probably an unfamiliar notation. In discrete space, we can look at it. This is what we'll look at next meeting. The discharge in the nth time increment is equal to the sum of the current precipitation, the previous, and the previous, and the previous, plus the unit hydrograph weights responsible for those. And so what we will do, the convolution integral will make more sense when you see this, when I explain this example. So what we will do next time is we'll pick up from here and we'll work through this example slowly enough to explain the different parts. So I am going to exit this screen, escape, go away. That worked out pretty good today, which doesn't always happen. And okay, so I am going to prepare to end the meeting, and I will see you all tomorrow at the same time. Hopefully I can get all these videos uploaded before too late tonight, and that'll give you a chance to stay caught up. A quick reminder, look at exercise set 2. Work through any of the lessons that the server allows you to, so that you can get the attempt acknowledgement, and I'll fuss with the grades if it misgrades you all. And there's a quiz number 2. So with that, if there's no questions, I'm going to go ahead and end the meeting for today. Thank you very much for your patience and attendance, and we'll pick up with more on unit hydrographs next time. Actually, that's going to work out pretty good. I can possibly rearrange the lesson count slightly. So with that, Have a great afternoon, and I'll see you again tomorrow.